This video is meant to serve as an introduction to what electric potential is. Now, before beginning, just a few comments about electric potential. It is finally the meaning of the volt. So nothing can feel more electric probably than when you're actually talking about volts like that. But this is what electric potential is. But unfortunately, in the study of electricity, electric potential in the volt is one of the most difficult concepts to get a good conceptual grasp over. So as you sort of are introduced to this concept here, it's just sort of tough to really understand what it is. In fact, in my opinion, it takes probably 5, 10, 15, maybe 20 years of sort of repeated exposure and conversations in different contexts and really seeing this thing work before you sort of have an intuitive grasp of what it is. So we're not going to go into any long labor here to really try to make some understanding of the volt. We're going to try and draw some analogies with gravity and just try and get some of the basic concepts out. And then in this video and others, we'll just try to use it a bit. But just keep in mind that a volt is an extremely difficult topic to walk around and say, yes, I understand what a volt is, because it is a hard one. Okay. So the first thing that we'll do then is let's try to just get an introduction to what a volt is going here. So what I have here is two sheets here. And what I'm going to do is I'm going to charge these sheets up. I'm going to get this sheet down here charged positively. Get a bunch of positive charge down here. This is something we've seen before in different videos here. And this upper sheet here, I'm going to charge negatively, like that. So that's what we have. And we know now from some of our other discussions is that when you have two sort of infinite planes or sheets near each other, an electric field will appear between them that looks like this. And we know from one of the very earliest videos here, the electric field lines go out of positive charges and into negative charges. They look something like this. So this is what the electric field lines are going to look like. And we know, although we're not going to belabor this point, we also know, like a little equation, that the magnitude of the electric field is sigma over epsilon. You can review a past video to figure that out. Remember, when you get two sheets near each other, there's no field here and no field here, all the fields in between, and sigma would be the charge density on either plate. So that's all something that we've seen in different videos, but we're not going to belabor it because we're trying to get some ideas of the potential out. So the question then before you then is, how would you get two infinite sheets to be charged up this way, one negative, one positive like that? That's sort of the issue. Well, one way you could do it is actually, believe it or not, with a battery. This is the 9-volt battery, so there's that voltage coming on again. And whenever you look at batteries here, they always have two terminals, this one and this one. And it turns out for the 9-volt battery, this terminal, the smaller one here, is the positive, and the larger one there is the negative. And so you could actually get this thing charged up with a battery like that. So why don't we just sort of draw that in here. So here's the battery here. It's a 9-volt battery, and there's a positive, negative terminal. And to get it charged up like this, I'll connect the positive terminal to this plate and the negative terminal to that plate. So this configuration, if these two plates here were sort of made out of metal, like aluminum foil or just some metal sheets, would charge up as advertised, and an electric field would exist between them. So we have a little idea here now. Well, there's sort of your first application of a volt here, is that if you sort of charge some plates up here, it looks like there's some voltage across them or something like that. But let's just continue on now. So just, again, very difficult subject. So let's do this now. Suppose in the intermediary, in this region between the plates, we put a positive charge. I don't know where you're going to get this charge. It could be a proton or just some ball that's been charged positively. And we hold it here with our hands. And the reason why we have to hold it here is because this positive charge is near this positive plate. And we know that like charges repel, so this charge would very much like to repel away from this plate and fly upwards and slam into the negative plate where it could perhaps be neutralized. Okay? So we're going to sort of maybe let it do that or imagine doing that, but we're holding it here for now. And so what would happen then if we did let go is, of course, as we just said, the positive charge would follow the electric field line. Lots of ways of getting at that here. Either opposites repel, or you just remember that force is QE. So if we take the positive charge and multiply it by the electric field magnitude, which we have here, then the force would be positive and upwards. This thing is going to experience an upwards force, and it's going to start moving. And it's going to go up here, and just before it slams into the plate, maybe we'll call this its initial position and that its final position right there. You'd have to agree that something sort of odd happened here in our understanding of volts. When we're holding the charge down here, it doesn't have any energy. It's not moving at all. But when we let go of it and it starts to fly up like this, suddenly it's moving here because it had this force of the electric field on it, or it's been repelled by this lower plate, however you want to think about it. And up here at this point, it has some kinetic energy up here. So down here, sort of the initial kinetic energy is 0, but up here, the final kinetic energy is not 0. So the question is, where did that energy come from? And there's your first idea here of what a volt might be. It turns out that what happened to this charge here is it gained some energy from the electric field. It was accelerated by the field and gained energy that way. That's certainly one way to think about it. But the other way to think about it is it sort of went through a potential difference. There's electric potential. An electric potential. It went through an electric potential of 9 volts. Because the positive plate is sitting down here and the negative plate is sitting here. But remember, the whole thing was connected to a 9-volt battery. So there's something sort of different about the potential down here at the lower plate versus the upper plate. And it appears as if gaining energy like that and slamming into this upper plate here, it appears as if the positive charge has gained some potential energy or potential. But in either case, you could think of it as sort of being at 0 volts down here at this lower plate. This lower plate might be 0 volts. This plate might be 9 volts up here. So just due to the fact that the charge went from 0 volts up to here, the charge is now at, you could say, at 9 volts. Guess what voltage would be right at the center there? Right, 4.5 volts. So that's sort of an idea, a little bit of indicator of what a voltage is here. And so if we just summarize here, you could think of this thing here as electric potential, kind of like the something related to but not the same as, I don't know, maybe the potential energy or just energy of a charge. That might be one way to think about it, but no matter how you dice it up, you have to admit that just by putting the proton or the positive charge in between these plates, by just letting it go towards this other plate here, it gains some energy. And in one view here, the energy that it gained would be the potential. So what we'd like to do then here is another couple things, is maybe to address the issue of then, well, if you charge these plates up with a battery, put a charge in there and it flies up here, and we're sort of saying all this stuff about how it has some energy now or it's at 9 volts, what exactly does a battery do then? So how is it that just by connecting this thing to a battery now, am I able to put charges in between plates here and have those charges pick up energy? What does a battery do to do that? Well, one of the best analogies that we have for what batteries are here is actually, so a battery here. A battery sort of can be thought of as a charge escalator. So an escalator, of course, moves people up and down floors, like in a shopping mall or something like that. So if you just have this battery sitting here like this, so here's this battery here, and it's a 9-volt battery and has a positive and negative terminal on it. The way you might think of what this is here internally, of course, this isn't exactly at all what's in there, but it's just a conceptual way of understanding this rather difficult subject here. It's a bunch of stairs like this. Here's the stairs, or moving steps, or whatever your idea of what an escalator is here. And you could say that maybe the negative terminal is down here, and the positive terminal is up here. So this would be like, I don't know, negative or 0, and that would be 9 volts up there. What happens if you're a charge and you come in here like a proton or something like that? You sort of go up, up. The battery lifts you up like that, and by the time you come out over here, you're still the proton, but you're at 9 volts. When you went in here as the proton, you went in at 0 volts down here. But when you came out, you were at 9 volts. That's actually what a battery does here. So when you think about the battery as it's connected over here, what it's actually doing is elevating charge to go between 0 and 9 volts. Now things are just a bit backwards here because you might think of the positive plate as being a bit higher in potential here, but that's actually what's inside the battery here. So we can just maybe redraw this thing like this here as sort of the charge escalator. That is the best mechanical analogy for actually what these batteries do. So you connect these two pieces of metal like this, and however you think about it, you could think about as these plates are initially neutral, and what the battery did was, remember that positive charges are never the ones that move, it's always the negative charges. So you might imagine that the battery started to suck little electrons off of this plate here, elevated them, so that when they left the escalator here, they were at 9 volts, and then deposited them, sort of put them all on this upper plate right here. And because we remove the electrons from the lower plate, it gets this net positive charge, and there's a negatively charged plate at the top there. But all these electrons have been energized. It's like they're on the second floor of a building at 9 volts, down here at the ground floor at 0 volts. So that's sort of a good analogy with what the electric potential is and what batteries do and how these potentials are created in circuits and so on. So just to continue on a bit, what we'd also like to do then, as I wrap this video up here, is let's just make some analogies with gravity, because gravity is probably something you're kind of familiar with. So what we'll do here is sort of make like a 2-column sort of page here. So what we have here is the ground. This is the good old earth here. And we have a ball right here, okay, the earth and a ball. And then what we have down here is almost like what we just drew previously. We get a positively charged plate like this and a negatively charged plate up here. And the reason why we need these both plates is because we need that nice electric field. So a couple things are going to happen here. Actually, what we'll do, I think, in case of the ball here, is why don't we just reverse two items right here. We'll get the ball. We'll put the ball up here, and let's put the positive plate up here, like this, and the negative plate down here. Let's do this instead. So this is a ball right here. Nothing to do with electricity, but just very good with common sense. And what we'll do in between the plates over here, the capacitor that we've all charged up, is we'll put another proton here. So things are a bit different. So everything's sort of drawn to the same scale and so on and so forth. We'll hold the ball here, we'll hold the proton here. And the question before you then is what happens when we let go of the ball? And what happens when we let go of the proton? So if we're holding the ball here and we let go of it, I think you probably know what happens. The ball is going to fall. It's going to go all the way down to here. And a couple of things are going to happen. Up here, the ball had some potential energy. You probably remember from your mechanics class, mgy, where y is the height of the ball. But then when the ball falls all the way down and hits the earth, it can't move anymore, so now it doesn't have any potential energy. The potential energy down there is going to be zero. That's what happened to the ball. What about the proton? Well, the proton up here is right next to this positive plate, but we're sort of holding it with our hand, or so maybe our hand's even shaking because we're just buzzing with energy. The ball would just love to get away from that positive plate, but we're holding it. It can't move. Just the way this ball would just love to fall as soon as we release it. So what happens when we do release the proton? Of course, the proton here, or the positive charge, is of course it also falls down towards the negative plate, ends up getting all the way down there, and so the proton or the positive charge is sitting down there like this. So you might say up here that the proton had some potential energy. Now, we don't quite know what that potential energy is. We have to work on that. But the potential energy on here is going to be zero, because either it gets neutralized as it slams into the plate, or it's just stuck on this plate here, just like the ball is stuck on the ground, and can't move unless someone came in and gave it some energy once again. Now, the issue is like, why did the proton fall? Well, the proton fell in between these plates, again, because of that electric field that exists between these plates that points down like this. That's why it fell like that, sort of sitting between the plates. Now, you might ask now, why did the ball fall? Well, the ball fell because of the so-called gravity field, which is in here. Now, we're having trouble figuring out exactly what gravity is and how it works, but as far as we know, there's maybe some connection between masses and two masses, like the big mass of Earth and the ball right here. This field called G, gravity, and that's what caused the ball to fall. So see, there's a lot of really strong analogies here with potential. This is gravitational potential over here, losing potential energy fall. This is electric potential, that volt over here. You started up here near this plate, which is maybe charged up to 9 volts, and you went all the way down here to this plate, which is maybe at 0 volts or something like that. So, of course, it's the battery that would cause this to happen. And so if you can imagine getting this thing to charge up with a battery, which might be like a little charge escalator once again, it'll sort of go up like this. And so in this case here, what might have happened is when it was connected, you could think of positive charges being removed from this lower plate here, being elevated up to 9 volts here and deposited on this plate, where this one remained at 0 down there. Of course, we know the positive charges don't actually move in these processes here. It's always an absence of negative charges, but the opposite could also hold, where we could think that the electrons were deposited down here. But that's just the way it seems to work. Let's just go with the positive charges and moving to keep the analogy going. So for whatever reason, the battery, it would just sort of create a higher energy electric state up here than the lower one. And we can see that when we put a positive charge in between the plates and cause it to move. It falls down like that. It goes from some higher potential to lower. Now, these U's here, just to be careful here, are not electric potential. These are potential energy. And these have units of joules right here. So we still quite haven't gotten to the volt yet. It's just sort of that difficult of a subject. So we'll wrap this video up here now with just against word of the wise here. This volt here is a difficult subject here. We have some parallels with gravity here, following the gravitational field or following an electric field here. The volt or electric potential is sort of what a battery is able to deliver to a circuit. And the odd thing about it is that as difficult as volt is here, these volts are actually what a voltmeter delivers to you. So if I turn this thing on here and sort of measure it, my 9-volt battery here, I should get a number near 9, although I think this battery is just a tad bit dead. But if I do this right here, and I connect the voltmeter to it like that, I get about 8.12 volts. So the battery looks like it is sort of dying. It's supposed to be a 9-volt battery, but according to this voltmeter here, this battery is able to elevate charges to a maximum height of 8.12 volts. So if I connected the battery to these plates and then put a voltmeter across it like that, I'd measure 8.12 volts if they were elevated with this particular battery. And we're going to close this video with one last concept then, which has to do with these voltmeters here. Whenever you look at a voltmeter like this, they always have 2 leads on them. There's always a red lead and a black lead. Always 2. There's never just one. And if you even look at the voltmeter itself, there's always 2 places to plug things into the voltmeter, never just one. Let me just give you a little analogy about why that may be as we end our introduction to voltage right here. So again, we'll have the gravity on this side and the electric on the other side. So here's the gravity side right here, and suppose there's a ball up here, and the ball is in H above the ground. And I know the potential energy the ball has here is given by mgh. So the question is, how did I measure that H? Well, the way I would measure the H here is maybe with a yardstick. A yardstick is something that looks like this and has all those little lines on it there, or a tape measure or whatever I want to do here. But the bottom line is that the yardstick has two ends, doesn't it? It always has an end that you have to put on the ground and an end that you have to put up near the object you want to measure. Same thing with a tape measure like this. Tape measure, of course, a little square thing like this with a tape that comes out. But you always have to put this tape on one side, like hook it onto something, like maybe first here. Then you pull this thing back to the thing you want to measure. And, of course, this distance here is, like, say, maybe H, the thing that you measure. But the point about both these is always two ends. 1, 2, 1, 2. You always need that reference to measure. So you can say the ball is a distance H, but relative to what? Well, the ground in this case here. And that's exactly the way voltmeters work too in their electric case here. So if I had something like those plates charged up like this, so here's positive, 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 positive. Here's a bunch of negatives down here, negative, 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 negative like this. If I wanted to measure the potential across these two plates, well, I couldn't use a yardstick anymore because it's an electric thing here, but I would have to get a voltmeter out. And I would put one of the leads, usually the black one, right there, and I get the other lead, usually the red one, up here. But the point is that there are two of them, and it's only in a case like this here that I'd actually be able to measure on my voltmeter and see the 9 volts. There's sort of another analogy with you with what a voltmeter does relative to the yardstick. Two ends of a yardstick to measure relative to some starting point like the ground, two leads on a voltmeter to measure the voltage at some point relative to the other point. So that's another thing about electric potential, and that's why it's usually called, most correctly, potential difference. That's usually what it's called, because you never measure the potential directly, but it's always a difference relative to some other point.